Okay, I think there we go. 11 a.m. on a Monday. Welcome back. Thank you for coming. I had left you guys with circulation, and I blah, blah, blah about flux, and now I'm going to be more definite about flux, okay? So, I'm just finishing writing this because I'm going to do a compare and contrast in a moment. So the flux, when we talk about the flux, we talk about the flux of a vector field through a curve. And I talked about how it'll be a little different when we go in 3 dimensions because it'll be the flux of a vector field through a surface. We'll need to do surface integrals then, okay? Right now, we're just doing line integrals around a curve. And what you have up top there is my big arrows represent some arbitrary vector field f. And then I create a curve C, and the outward normal to C is what you understand is perpendicular to the boundary. Now, I haven't constructed the outward normal for you. This is not the normal that we did in chapter 13. If you remember, on a curve, the normal to the curve that was defined by the curvature was basically the way the curve is curving, right? If you're curving to the left, the normal is to the left. If you're curving to the right, the normal is to the right. That was a different normal. I used capital N to denote that normal. This is still a normal, so it must be parallel to that previous normal, right? If it's a normal, it's a normal, it's a normal. But this one is always outward. And the point is, to know what is outward, you have to know what is inside. And to know what is outward, to know what is inside, you must see the whole curve, right? If you just see a part of a wall, you don't know which way the room is. You got to see how the whole wall encloses the room, okay? So this outward normal is what we call a global property of the domain. You need to know everything. Well, you need to have seen the domain. You have to look away. Whereas the other normal, it was just a local property. You just had to calculate the derivatives at a point, and you could figure out which way the curve was curving. Okay? I don't know if that totally makes sense, but that's the difference between global and local. So the flux is defined in the book, and it's a very important quantity we're going to understand. The flux is equal to the integral around a closed curve. It makes sense only around a closed curve of f dot so this is the normal component of the vector field, line integrated around the curve. And the way you really do it is like this. And this should be a dot product, I apologize. You parameterize the curve, r of t. You evaluate the vector field along the parametrization of the curve. The normal depends on where you are. That's just, it's this way, that it's just where you are along the curve, so it depends on t. And of course, ds is the magnitude of dr dt multiplied by dt. Okay? Now, I'm comparing that to the circulation, and what you see, the only difference in the definition is the circulation is the tangential component integrated around the curve, whereas the flux is the normal component. Now, I'm just working out the circulation one step to look like this aspect of the normal, of the flux. Circulation versus flux. And let's go one more step, because in the circulation you can combine these two terms. You can't do that in the normal exactly. But in the circulation you can combine these two terms. And the combination of these two terms gives you the following. The integral from t0 to t1, f vector, I'm going to suppress the argument, t hat times the magnitude of dr dt is simply dr dt. Right? Because t hat is dr dt divided by its magnitude. So this product is dr dt. So this is f times dr dt times dt, which is often written, the integral from t0 to t1, of f dot dr. This is often written this way. So the circulation will be written this way. I find this, especially when you're starting to understand these integrals, I find this to not be helpful. Okay? I find this to not be helpful. This is really the most common way you'll solve the problem, or maybe this way. The time parametrization. This FDR is along the curve, you're going in the dr direction, and this is the component of f in the dr direction. That's what it means. Whatever version of this you find convenient is fine with me. Okay. So that's the flux. Now let's, so the issue is the normal. The issue is the normal. How do we compute the normal? Okay? So let me compute a normal vector for you. Let's go over here, and I have a curve. Is parametrized by t. So it's given by r of t is equal to x of t I hat plus y of t j hat. We know the tangent vector is parallel to dr dt, and that is dx dt I hat plus dy dt j hat. And so if I want the unit tangent, I write dr dt divided by the magnitude of dr dt. And when you have a curve, everybody, when you have a curve, let's say this is the tangent vector. But had you chose one parametrization, the tangent vector would be going this way. Had you chosen the other parametrization, the tangent vector might be going the opposite way. So the way that the tangent vector is going sort of depends on your parametrization. Okay? I've been trying to use these counterclockwise parametrizations because counterclockwise is a convention that we will have, that we will keep, that we will use. Okay. Now, I want you to look at this, the dr dt, and let me draw that piece of the curve again. And here's a tangent vector, t hat. Okay? My normal vector of a curve is perpendicular to t hat. So it's perpendicular. Bada bing. N hat. Okay? There's the normal vector. So in order to construct a normal is parallel, if you don't mind, to the perpendicular parallel to the perpendicular of dr dt. Right? The normal hat is perpendicular to t hat, which is proportional to dr dt. So let me say not the unit normal, but I'm going to say a normal vector, n vector, because it's not going to be a unit vector right now. It has to be proportional to something that's perpendicular to dr dt. And the easiest way to make a perpendicular is to flip the order of the components, and put a negative sign. Okay? So I'll tell you right now, I always just do this. The normal is proportional to this. Okay? What did I do? I took the dy dt from the j hat entry over there for the same curve. I put in the I hat entry. I put the dx dt over here, and I switched one of the signs. Take the dot product of this vector with that vector. Right? Well, the first component term will be dx dt times negative dy dt. And the second term will be dy dt times positive dx dt. So they'll add to be 0. So this is clearly perpendicular to t hat. Now the only question remains, is it outward or is it inward? Which direction is it going? And that really is, you got to be a little careful about that. That depends on your parametrization. Okay? That depends on your parametrization. So I'll tell you the truth. I always forget. I don't have this thing memorized. Okay? Life's too short to have this thing memorized for me. Okay? So what do I do? I go back to the circle. Okay? I remember my circle. And let me just do the unit circle. R of t is equal to cosine of t I hat plus sine of t j hat. Okay? So there's R of t. And this is at t equals 0. And we know that dr dt is equal to negative sine t I hat plus cos t j hat. By the way, this is the counterclockwise circle. So we know that the tangent vectors are going to be going like this, okay? And if you want to, when in doubt, just double check, okay? At t equals 0, notice at t equals 0, r of 0 is equal to 1 I hat, right? Because this is 1 and that's 0. So you're over here at t equals 0. At t equals 0, dr dt is equal to 0, it's just j hat, is equal to j hat. And so it's pointing up. So you are here and you're pointing there. It's just a nice way. And so you know, you're like, okay, by continuity, this thing's got to keep going around and around. So this is counterclockwise. Okay? Well, now I'm going to say, what's the normal vector? N vector, not the unit normal, because this wants the unit normal. The flux wants the unit normal. Just the normal vector is, I'm just going to swap and change one of the signs. So I'm going to put the y component in the x place. So I'm going to put a negative cosine t I hat, and the x component in the y place, which is going to be minus sine t j hat. Okay? So all I did was I took dr dt, I swapped the two components, okay, and put a negative sign on the first entry. That's what that told me to do over there. Okay, now you can see, take the dot product of this with that, it's 0. But now let's evaluate n hat at t equals 0. At t equals 0, n hat is equal to negative I hat. Right? So I go to t equals 0, which is right here, and n hat is equal to negative I hat. And I was, my wife really loves to say this, I was wrong. I was wrong. Okay? I hate being wrong. I don't like to be wrong. I was wrong. I told you I didn't memorize this thing, right? But I understand what perpendicular, why? This is inward normal. I've just shown you the inward normal. This is the wrong normal vector. Okay? So now we're going to go. And I'm going to say, hey, look at this. Here I am over here. And I told you to put the negative sign over here on the first one. Right? Well, professor was wrong. Write it down. You get to, like, be proud. And I'm going to switch the negative sign. It was either the inward or the outward. It had to be one of the two. And I'm going to go back over there and say, oh, had I switched the negative sign, I would have kept the cosine over here and swapped this sign. And now this is clearly the outward normal. It's positive I hat at t equals 0. Now I've got the positive I hat. Okay? You guys cool with that? And so, if, this is what we're learning from this, if you have parametrized the curve counterclockwise, so the curve in a counterclockwise manner, then the outward normal is, lifting this board up, the outward normal is, stay on this board. Don't go, don't go, don't go. I'm telling the camera person, I think. And the outward normal is n hat is equal to dy dt I hat minus dx dt j hat divided by the square root of dx dt quantity squared plus dy dt quantity squared. Okay? That's how you construct the normal. But there's a big if at the beginning. If your original curve was counterclockwise. Out is out is out is out. It didn't care if you walked around that curve counterclockwise or clockwise. Okay? Out is out is out is out. So this is true if this is counterclockwise in the net counterclockwise. Because you can have complicated curves which are doing this, and you don't know which way is clockwise or counterclockwise until you decide to close the curve. Tricked you. Okay? And you mean counterclockwise in the net. Because we know which way is out, right? Well, maybe you don't. I can color it in. And I'm not notorious for not being able to stay in the lines. I got a C in kindergarten for not staying in the lines. Okay? There's in, and there's out. That I'm cool with. Okay? And then I know that this is going to be counterclockwise. Out. Okay? But it looks like it's sort of clockwise over here. Because you can't tell on a local patch of curve. You need the whole piece. It's okay, pick it up. Not a biggie. Okay, that's a beautiful curve, isn't it? So folks, the truth of the matter is you have a lot to memorize in your life. This is not something you should necessarily memorize. Okay, I can't memorize it. I haven't memorized it. What I'm going to ask you to do is understand what out and in is. And what the best way to figure this out at all times is write your parametrization down, whatever it does, and then test one of the vectors and say, was that a counterclockwise or a clockwise vector? And if you need the outward normal, swap the components and change the sign of any one of them, and then test, was that an outward or an inward normal? If I change the wrong sign, I'll go back and fix it. Okay? It's not a big deal. As long as you know what you're doing. Does this make sense to people? Is it too easy? Okay. Do I go ahead and compute some flux? Should I do a homework problem? Should I do all the homework problems? Sorry. Okay. Okay. Because you saw that doing the square could be just like, because it's piecewise defined, it takes a little bit of time. So I'm going to do a circle, okay? Can I do the circle again? And I'm going to do that same example that I did last time. What did I do last time? I computed circulation on two vector fields of two different curves. But this time, I'm just going to use one curve. I'm just going to use the circle, okay? I hope these examples are edifying. I know they're algebraically more simple, but they don't get that much more complicated. So 3 vector fields, okay? 3 vector fields. Which 3 vector fields? Maybe I'll go for 4. I'm going crazy. Let's go for 4. 4 vector fields. Okay? Let's do 4 vector fields. Okay? The first one I'm going to do is F is equal to U0 I hat, where U0 is a constant. Then I'm going to do G. I'll give them different names, okay? This time that way. Okay, G is going to be my radially outward pointing vector field. So G is going to be alpha xi hat plus yj hat. H is going to be omega times xj hat and negative yi hat. Okay? And by the way, I hope you're seeing the pattern. I gave you these 2 vector fields. They are perpendicular to one another. Circulation and flux measure perpendicular components. So there will be a symmetry It's too exciting. Flux is just so exciting. And let me call this one I. I'm going to use the I vector field too. Okay? I is that last vector field. Remember the one that was on hyperbolas? I kind of did that as an example. Went up like this, and there was like the pinchy one I talked about in fluid dynamics. It was one of the basic ones I talked about. Okay? So this is going to be some beta of x I hat minus y j hat. Okay? And my curve is just going to be the circle of radius a. So c is r of t is equal to a cosine t I hat plus sine t j hat. Okay? And I'm going to calculate the flux through this curve. So the first thing I need is dr dt. And that's equal to negative a sine t I hat plus a cos t j hat. That's the tangent vector. It's not the unit tangent, right? And then what did I say? Well, the normal vector, not the unit normal, but the normal vector was swap them. There it is. I kept it on the board. Yay. Swap them and switch the sign, right? Swap. So the a cos t goes here, I hat, and then this one goes over here, j hat. Okay? By the way, the circle that's centered on the origin is the curve whose normal is everywhere parallel to its position vector, right? Because if it's centered on the curve, your perpendicular is radially outward. And so this is actually exactly equal to that. Okay? Now this is not the unit normal. I have to take the unit normal, I have to divide it by its length. But that's pretty straightforward. N hat, the length is clearly a. So n hat is cos t I hat plus sine t j hat. Okay? So now I've computed the n hat. I want to write it this way. So I'm going to need the magnitude of dr dt, and I just divided by it, so I better know what it is. It's just simply a. Okay? So as you can see, just as in the circulation calculation, where when you took the normal, you divided by the magnitude of dr dt, but then you multiplied it again because of the line integral, the same thing happens in the flux calculation. See, I'm going to be multiplying this by this. To get this, I just divided by a, but I'm multiplying by it again. Okay? So that'll save you some time, that observation, that fact. It just happens over and over again. Okay? So the integrals that I need to compute, I'm going to do them over here. The flux for vector field G, no, F. I guess I should start with F, right? Let's at least go alphabetical. Okay. So, example 1, for F vector, the flux is equal to the integral from 0 to 2 pi of the vector field u 0 I hat. It's the constant vector field pointing to the right. Okay? Dotted into the unit normal multiplied by dr dt. Well, I'm just going to write that a. I'm going to just swap the order. Times cos t I hat plus sine t j hat. So it's this integrated with respect to t. Well, I hat dot I hat is 1, and I hat dot j hat is 0. So the a comes out, the u0 comes out, and you're left with the integral from 0 to 2 pi of cosine of t dt, because only the I hat component survives. Now, this is 0. This is clear. The integral of cosine from 0 to 2 pi is 0. Okay, that's 0. What's this saying? Well, it says on the left side of this vector field, stuff is coming in, and on the right side, it's going out. So the net flux, the net stuff that's remaining in there is 0. That's what flux measures, the stuff. Okay? I'm using u naught as having units of a velocity, but really u naught has the best u naught has units of momentum density, which is velocity times mass per unit area. Okay? So if I had done velocity, well, if it had velocity times mass per unit area, right? So I did this last time, didn't I? I did the unit check. If U naught has, so if the vector field has velocity multiplied by mass times unit area, that's momentum per unit area. When you integrate that with respect to length, you get another length on the top. So you got length squared times mass divided by length squared times time, which makes it mass divided by time. And so then it really tells you this is the amount of stuff that accumulates or actually leaves the domain. It's mass per unit time leaving the domain. That's what flux is, the net mass per unit time leaving the domain. And I had a conversation with some engineers that in engineering classes, engineers say they use not this integral, but they use the vector field to talk about flux. That is not the flux. That's called the flux density. Okay? So as engineers will sometimes use the word flux, but they really mean flux density. So write that down when you get confused in your engineering class, okay? And it has to do with the fact that, you know, people just drop words sometimes. Okay? And one field will drop words, and we get a little sloppy with the way we define things, okay? We don't, they do. Oh, we don't. We get punished for being sloppy. We do. Engineers don't. Okay, that was F. Let's go with G. Example 2 for G. Go for G. Okay? Well, the flux equals the integral from 0 to 2 pi, and I'm going to write this out first. Alpha x of t I hat plus y of t j hat. That's the vector field. A times cos t I hat plus sine t j hat. That's dot product. This is the magnitude of dr dt. This is n hat. And then I have to integrate this with respect to t. And I have to evaluate x of t and y of t. And of course, to do that, you just have to use the original r of t, which in this case is pretty easy, right? It's just a cos t I hat plus b sine t j hat. So this is a cos t. This is a sine t. I think I said b, but I meant a. A cos t, a sine t. So this is going to give me alpha from here, a from here, a from here. That's the a squared. The integral from 0 to 2 pi, this is cos t times cos t plus sine t times sine t. So that's cos squared t plus sine squared t dt, which is equal to 1. So the whole thing is 2 pi times alpha a squared. And remember from last time how I factored it. I got the 2 alpha and I got the pi a squared. And I said it was no coincidence that this was happening. Okay? 2 alpha is associated with this vector field, and the pi a squared is associated with the area, well, it is the area of the domain D. And when we get to Green's theorem, this will be fully clarified. Vector field 3 is the H vector field. But I'm not actually going to bother computing H. Why am I not going to bother computing H? Because 1, 2, 3, it is clear, Claire, it is clear that n hat dot h is equal to 0 at each point. Each point along the curve. Right? By now you have intuition about what H is. It's the swirly vector field, right? H is my swirler. Okay? And n hat, so H is tangential to circles, therefore, and n hat is perpendicular to circles, so they're perpendicular to one another. So the flux because it's at every point equal to 0, then the total flux, which is the integral of a bunch of zeros, is 0. Okay? Case 4, right? Case 4 is the I vector field is equal to beta x I hat plus minus y j hat. I wrote this one down as one of my basic vector fields because it was a basic fluid dynamics flow. And if you remember, it was these little hyperbolas. This is for beta positive. These vectors look like these little hyperbolas. Okay, this is the I vector field, okay? And then I'm going to integrate along the circle. Now you should see what's happening here, right? Just by looking at it, you can see that stuff's coming in, and stuff's coming out, and stuff's coming out. So if you believe my intuition, this might have the property that its integral is 0. So for the swirl vector field, the previous example, nothing was coming in or out at any point because it's perpendicular at all points, right? It was swirling along. This is going to work out that it's going to be 0, not at every point because stuff is coming out and in, but it's going to integrate. It's going to average to 0. Okay, so let me do it. So here we go. I got my n hat. So the flux is equal to the integral from 0 to 2 pi beta x of t is a cos t. Now I'm substituting it in I hat. I'm running out of space here. Actually, just I'll lift the board up. So the flux is equal to the integral from 0 to 2 pi beta times a cos t I hat minus a sine t j hat. That's the x I hat minus y j hat dotted into a times the normal vector, which is cosine t I hat plus sine t j hat. And then I have to integrate that with respect to t. There is an a common to everybody, and there is a beta. So this is beta a squared. See, that kind of happens a lot. That a squared is happening a lot in these simple examples, I acknowledge. But these are very canonical examples. Now this is the integral from 0 to 2 pi. I got the beta, I got the a and the a out. Cos t is cos squared t minus sine squared t dt. Cos squared t minus sine squared t. Okay? So there's a bunch of ways to think about this. When you have cos squares and sine squares, you should always think about, remember that cos squared t is equal 1/2 times 1 plus cos 2t, and sine squared t is equal to 1/2 1 minus cos 2t. And when you subtract them, cos squared minus sine squared is clearly cos 2t, but you could have done that with the double angle formula. Or you say cos 2t is cos squared t minus sine squared t. So this thing is cos 2t. And the integral of cos 2t from 0 to 2 pi is equal to 0. Because you're going over bump up, bump down, bump up, down, bump down. So it's equal to 0. And that shows you that the total amount of accumulation inside this domain is 0. That's the flux. So those are those three basic concepts. Are there any questions here? Okay. Nothing at all? Everybody had that down? I could have just skipped it? Okay, well, then let's move on. We're on 16.3. So section 16.3 is path independence and conservative vector fields. Path independence and conservative vector fields. Okay? So I think this is best motivated by going back to the example of work. Well, work is essential to this. But let's just do an example, okay? So let's do this example. E.g., m dv dt is equal to negative m g k hat. We've seen this one before. This is a particle under the influence of gravity. And our vector field, we're going to stay with our vector field in 3 dimensions, okay? We're going to keep V is in 3D. Everybody's in 3D right now. And we know the solutions to this thing. We throw baseballs, and we create parabolic arcs. This is, say, x, and this is the z direction. That's a sloppily drawn axis. Okay? Now, we constructed the work function for this. What did we do to do work? Well, we said, look, the force, what we did was we took the dot product of that with respect, we took the dot product of that with v. Okay? We took the dot product of the left-hand side with v. So the force is negative mgk hat. And we showed that when you dot product with v, you get m times magnitude of v of t squared divided by 2 minus m times v, and this is v vector, of 0 squared divided by 2. Took the dot product with v, and we integrated, right? Is equal to the integral from t equals 0 to some later time t of negative mg k hat dotted into v vector of t integrated with respect to t. Well, v is dr dt. And so this right-hand side is equal to the integral from 0 to t of negative mg k hat times the tangent vector t hat times the magnitude, which is the magnitude of dr dt, integrated dt. And this is the line integral, right? We showed that we said, hey, this is the line integral of f dot t hat ds. So I'm going to go up here. So therefore, the change in the kinetic energy, which is the left-hand side, is equal to the work done. And that's equal to the integral over the curve of f dot t hat ds. That's what we showed. That was the whole section on work. So that's fine and dandy. That's kind of nice. That's kind of nice. If you take a look at this integral depends on the curve, right? I also use this integral to define the circulation and the flow. But it clearly depends on the curve, because in order to evaluate this integral, you have to know where the curve is, right? You got to know where that curve is. But notice that in this particular case, and I'm going to put and in many, many others, and in many, but not all cases, f vector is equal to the gradient of some other function little f. Can I use little f? I'm going to use little f. What is that function? Little f is equal to negative mg times z. mgz. What's the gradient of little f? This is gradient 21c, right? Remember 21c, gradient and directional derivative. At this stage in the game, I would like you to remember the definition of the gradient, the definition of the directional derivative. You should understand those very well to be successful in this part of the class, okay? The gradient of a function is equal to the derivative of the function with respect to its first component multiplied by the unit vector in the first direction, plus the derivative of the function with respect to its second component multiplied by the unit vector in the second direction, plus the derivative of the function with respect to the third component multiplied by the unit vector in the third direction. Okay? If this is true, if in this case it is true, well, let's just see what this gives us. df dx is 0, df dy is 0, df dz is negative mg k hat, which is exactly the force that I was talking about, the right-hand side of Newton's law in this particular instance. Okay? As an interpretation, if you take a look at x and z, and I'm not going to draw the y-axis out, contours of constant little f are horizontal planes at constant z. They're horizontal planes at constant z. Very well. We move over here. So who cares, right? Like, so what? So what? What do we get here? Well, I'm going to plug this into the definition of this equation of the work here. So the work is equal to the integral along the curve of the gradient of little f dot, let me write it in terms of dr dt. Okay, I'm going to write it in terms of dr dt times the tangent vector times the magnitude of dr dt times dt. Okay? But this was the original velocity vector. When I derived this, this was v vector, right? So this is the gradient of f dotted into v, integrated with respect to t from along the curve, whatever the curve's parametrization is. Okay. Now, as they say, amici, romani, paesani. Now I'm going to do something, okay? I haven't really done anything. I've just been talking for like 45 minutes. I haven't done any new math for you at all. Okay? I'm going to do something here. What is that quantity in parentheses? Okay, so I draw your attention to me right now. Those of you who are sleeping, wake up. Sleepers awake. This is the moment you need to pay attention. Okay? What is that quantity in parentheses? I'm going to ask you to think about that quantity in parentheses. F is a function of x, y, z. Right? It's a function of where you are in space. It's a very simple one right now. But if you evaluate f along the curve is to let, when you evaluate f along the curve, that is letting x be the function of t, y is the function of t, and z is the function of t that give us the curve. Right? That's the functions that give us the curve. So the curve is r of t equals x of t I hat plus y of t j hat plus z of t k hat. So this is somewhat an abuse of notation, right? These correspond, with no argument, they correspond to the Cartesian coordinates of space. These, with the t argument, correspond to the particular x location of that curve at that given time. Okay? So these are functions of t, and these are not. But when you evaluate f along the curve, you evaluate that function of t. So this becomes some other function of t. It's a function of t. Now, what is the derivative of f with respect to t? This is why you did directional derivative. This is directional derivative. Okay? It's simply the chain rule. Okay? What is it? It says, take the derivative of f, little f, with respect to the first argument, multiplied by the derivative of the first argument with respect to t. Where do you evaluate this? You evaluate it along the curve. So this is a function, right? This is a function of little x, little y, little z, but you evaluate it at x of t, y of t, z of t. So it's evaluated at x of t, comma y of t, comma z of t. And then you do the same thing for the second component, df dy, dy dt, plus df dz, dz dt. Each of these these are clearly, the second terms are clearly functions of time, right? Because they're x of t, y of t, z. These are functions of little x, little y, of x, y, z that get evaluated as functions of time. What is this thing right here? This is the directional derivative in the direction of the velocity v. That's what it means. But what is it really? It's the gradient of f. Well, really, there's both things dotted into v. And that's the crucial understanding. The gradient of f dot v on a trajectory, which is that quantity in parentheses, is the time derivative of f, of capital F. And so this is equal to the integral along the curve of d capital F dt integrated with respect to t. But by the fundamental theorem of calculus, this is the antiderivative of the derivative. So this is f at t1, the end time, minus f of t0, the beginning time. What just happened? What just happened is that I had an integral along the whole curve, and technically to know what's going on the whole curve, I got to know where that whole trajectory is. And this said, no. When your force is a gradient, you only need to know where you started and where you ended. And what was this f over there, and what was this f over there? Well, stop. What did I say capital F was? You got to give me this minute, everybody. What is capital F? F is just little f evaluated along the curve. So this thing, this capital F over here, is just little f, which is negative mg. I'm using the example now. Z of t1 evaluated along the curve minus negative mg z of t2. And that was m of v of t1 squared over 2 minus m of v of t0. What did I say? Z of t1 and z of t0. This should be z of t0. Minus m times the magnitude of v of t0 quantity squared over 2. Pause. I'm going to rearrange this equation. I'm going to put everything that depends on t1 on the left-hand side. I'm going to put everything that depends on t0 on the right-hand side. And I've got m magnitude of v of t1 squared over 2 plus mgz of t1 over 2. Now over 2. No over 2 on that one. Is equal to mv of t0 quantity squared over 2 plus mg z of t0. This thing is the negative of little f. It's the negative of little f. Just trace it back. It's the negative of little f. There's little f over here. Little f is negative mgz. This is the negative of negative mgz because it's positive mgz. And this has a name. It's called V. It's called the potential energy. Or rather, what we have just discovered, everybody, is the following. When your force vector is a gradient, your work is independent of path. It only depends on where you started and where you ended. When you put it into the energy equation and rearrange, you can put all your end times on one side, all your beginning times on the other side, and it says this. The sum of this quantity plus this quantity is equal to the sum of this quantity plus this quantity, or whatever you had at the beginning is what you have at any other time. This combination is conserved. It is conserved for all time. And so we give this combination a name. This combination was called